right, we're going to look at lesson 12. So go to support material, and I would open up the slides and have these as we go through this. And then as we go through each of these things, you'll notice on the assignment, the first thing you'll do is as we describe each thing, I'm kind of going to give you a section to take notes. You're going to say what each term means, and then which letter we use to represent the term, and then give any type of equation that goes with the term. So let's go ahead and get started. This is going to be kind of a unique lesson. It's definitely going to seem kind of strange the first time you go through this. This is not all we're going to do on this. We're going to go into more detail tomorrow. And as backwards as this sounds, this is a concept that actually will begin to make more sense the more details we put together. So today I'm going to give you some equations. They might seem kind of random and obscure, but as we get more in depth, they'll make sense. So just make sure today you're getting used to what each letter what each letter represents, and then understand the equations that go with it. The idea here, these quantum numbers are used basically to locate an electron. So I mean, I guess I could put it like, imagine if there's a street with a bunch of hotels, and we have one number to represent which hotel you're at, and then we have another number to say which floor you're on, and then another number to say which room you're on, and then another number to say which bed you're sleeping in, right? With that, I could use a set with 4 numbers. I can narrow it down to exactly which bed you're in. That's the idea here. As we get through these sets of numbers, they help us to locate an electron. Okay, so our 4 quantum numbers, we're going to have the principal quantum number, the azimuthal quantum number, magnetic quantum number, and electron spin. We'll talk about N first, the principal quantum number. So this represents the energy level the electron is located in. So in your notes, you'll put that principal quantum number represents the energy level of the electron. We use N to say it in shorthand. And what you can do with this to figure out how many total electrons are in any energy level, whatever energy level you're at, you first square it and then double it. Okay, so whatever energy level you're in, it's almost like having hotels, and this is a way to figure out how many people could fit in a hotel. The higher the energy level, the more space it's going to have. The more people will be possible to fit there. So the energy levels begin at 1, and the highest they get is 7. If the electron if it's in ground state, which means there's nothing weird happening to the atom, then we go from 1 to 7. That's all we'll get for N. If something happens, there's extra energy, then the energy level can go higher than 7, but that normally won't happen. So using the equation to figure out how many electrons do we have at any energy level, you just do 2n squared. So look at what we do right here. If n is 1, you'll just do 1 squared. So you'll do 1 squared, and then you'll do times 2, and you'll get 2. If n is 3, then you'll do 3 squared, which gives us 9, then times 2 gives us 18. If energy level is 5, you do 5 squared to get you 25, times 2 gets you 50. Okay, so that's the equation. If it's how many, so looking at your problems, your first 3 problems, how many electrons can you find when n is equal to? So go ahead, do 1, 2, and 3. So pause it, try 1, 2, and 3, and then I'll go through it quickly with you. Okay, so number 1, you do 1 squared, which is 1, times 2, which gives you 2. Number 2, n is equal to 4. 4 squared, 16, times 2, 32. Number 3, n is equal to 7. 7 squared, 49, times 2, 98. That's all you do for this, okay? So that's the principal quantum number. So we know what energy level the electron is in, and we can figure out how many electrons could fit at that energy level. But especially if you're doing, like, look at what we just figured out. If you're in energy level 7, there could be 98 electrons there, and it's organized where they go. So how do we figure out where the electron is at inside that energy level? So the next thing we have is this, the azimuthal quantum number, also called L. And L tells you the sublevel the electron is in. So once we know we're at a particular hotel, I would say sublevel is like discovering which floor of the hotel we're on. The equation we get for this, for whatever n is, so the bigger n, or the bigger the hotel, the more floors you'll have. The idea here, whatever your number is for n at that energy level, the maximum number you'll have for L is just one below n. So if n is 4, the highest sublevel is 3. If n is 7, highest sublevel is 6. So it's just n minus 1 tells you the highest L will be. Now the sublevel, or the L, it starts at 0, and the highest it gets depends on which energy level we're talking about. So that's our only equation for this one. So you'll put for your notes, azimuthal quantum number represents sublevel. We call it L, and the equation is that highest L equals n minus 1. So right here. This is something that's not going to be super important right now, but it will come up a lot in the next couple of days. So what we do, because there's so many numbers, right, we could say energy level is 1, sublevel is 0. Soon we'll get to orbital, and we're going to get all sorts of stuff. So what we do for the second concept here, out of these, the second one right here, the azimuthal quantum number, instead of having numbers to represent it, what we've done is we've picked the most common numbers, the first 4, and instead of writing 0, 1, 2, 3 to represent the sublevel, we actually, I know this seems confusing, but we have letters. That way, when you write this all out, instead of having like energy level 3, sublevel 2, orbital 3, spin 1/2, instead of having all numbers, the second one, instead of 0, we write S. Instead of 1, we write P. Instead of 2, we write D. 3, we write F. This probably will be the most confusing thing on here. You're thinking, what in the world? There's so many numbers and stuff to keep track of. When we start putting all this together, I will remind you of this then. So for now, you can forget about this. Don't try to remember this. I just want to bring it up now. That way tomorrow, actually not tomorrow, the next time we go over this stuff, I'll bring this back up, and then you'll be like, oh, I do remember hearing a little bit about that, and it'll make sense when we start putting all this stuff together. All right. So let's go look at the problems. So I want you to try to do 4, 5, and 6. So pause it, do 4, 5, and 6, and then come back and we will discuss what we get. Okay, number 4. When n is equal to 1, what's the highest L is going to be? Just do 1 below that. 1 minus 1, we get 0. N is equal to 4. 4 minus 1, the highest L gets is 3. N is equal to 7. 7 minus 1, the highest L is going to be a 6. Okay? So I hope these equations are pretty easy. I can understand for you picturing exactly what this is doing is what's tough. And that the whole picture will come as we get a few more days into this. Okay, next up we have the magnetic quantum number. We call this M. And M represents the spatial orientation of the orbitals, or we'll just call M represents the orbitals. Okay? So M is the orbital. So if we're talking about organizing where something is at, you can imagine the energy level tells us which hotel the electron is in. Once we know the hotel, the sublevel tells us which floor. And now that we're at a specific floor, we got to talk about what kind of rooms we have. So this is like having the room number. Now the thing with the magnetic quantum number, the thing with the orbital, is it can be negative, 0, or positive. So the number of possible orbitals you have is going to be, it depends what sublevel you're at. The higher the sublevel, the more orbitals will fit. But whatever sublevel you're at, you double it, and then you add 1. And that's the number of possible orbitals. The reason it works like this, look at this. So if L is 4, let's go ahead and use the equation. If L is 4, remember what I said you do? You double it and add 1. So let's do 4 times 2 is 8, and then add 1, we get 9. So if the sublevel is 4, if L is 4, how many orbitals are we going to have? We're going to have 9 possible orbitals. Okay? So that doesn't mean orbital is number 9. It means there are 9 orbitals. It's like saying if you're at the 4th floor, you're going to have 9 rooms. Now, what are the room numbers? What are the numbers of these orbitals? And this might explain to you why this equation 2L plus 1 works. What you actually do to determine what we're going to call each orbital, if we're at 4, you would start at -4 and end at +4 and pick every number in between, including 0. So look, 1, 2, 3, 4, 5, 6, 7, 8, 9. See how that's going to work? If we're saying L is 3, okay? Well, then we're going to do 2L plus 1, and we would get 7. Okay, so we'd say if L is 3, how many orbitals are you going to have? You're going to have 7. And the names of them would be, start at -3, then -2, then -1, 0, 1, 2, and 3. So go from -3 to 3 and pick every number in between. 1, 2, 3, 4, 5, 6, 7. So you see how that works every time. If you actually would have an easier time, instead of just remembering 2L plus 1, if you want to actually start at 4 and go all the way to -4, or if it's asking for 7, you go from -7 to 7, count how many are in between. That's also okay. So here's what we just did for 3. We'll get to spin in just a second. So for your problems, I want you to go ahead and do 7 through 9, and then pause, and I will go over it. That will be the end of the problems, but after that, make sure you listen for the very last, the 4th quantum number. While it's not on any of these problems, it will come up a lot tomorrow. Go ahead, do 7, 8, 9. I'll go over it, and then we'll wrap up the slides. Okay, so how many orbitals do you have when L is equal to 1? 2L plus 1. Okay, so 2 times 1 is 2, plus 1 gives me 3. L is equal to 4. 2 times 4 is 8, plus 1 gives me 9. L is equal to 7. 2 times 7, 14, plus 1, 15. All right, so the last thing, so the way I put it, a lot of hotels have 2 twin beds, a lot of standard hotel rooms. So let's say the energy level is the hotel you're in, sublevel is the floor, orbital is which room on that floor. Now in a room, in each room, you can only have 1 of 2 beds. That's the idea here. So once you know the energy level, the sublevel, and the orbital of the electron, then it can only have 1 of 2 spins. It can either have +1/2 or -1/2. That's all you're going to have for the spin. And this just represents if it's spinning clockwise or counterclockwise is the way you can think about it. It can only spin 1 of 2 ways. When we do this stuff, and this will come up tomorrow, the next day, +1/2 is drawn as an up half arrow, -1/2 is drawn as an upside down half arrow. Once again, this is a rule that you'll see a lot of tomorrow. The Pauli exclusion principle, this tells us that each orbital can only hold 1 electron with each kind of spin. So say if I'm at energy level 3, sublevel 2, and then orbital 0, right? So that's like my hotel floor and room number. At orbital 0, you can only have +1/2 and -1/2, and that's it. So you can have 2 electrons, one spinning in the positive direction, one spinning in the negative direction, and then that orbital is full. That's it. So what this means, the Pauli exclusion principle, no 2 electrons can ever have the same 4 quantum numbers. So if 1 electron, the quantum numbers are 3, 2, and 0, then the last quantum number for one of them has to be 1/2, for the other has to be -1/2. And since the orbital 320 is full, you're not going to have any more of that quantum numbers. Once again, I know this is a lot, but so here's some practice. I know that this is a lot, but just make sure you can do the problems. And then once you can do the problems, you're good for today. And we'll get into more detail tomorrow. So give this your best shot. If you have any questions, please email me.